All right, I'm here to present R2DSP Project 4, the last section. Section 4 using a cascaded bandpass filter using LC-Pi circuits for both low pass and high pass. So there must be two cascaded low pass LC-Pi filters and two cascaded high pass filter, two cascaded sections of the high pass LC-Pi filter. So the first thing we should go over is a little bit there about the LC-Pi filter and how I designed the LC-Pi filter. So if I scroll down here, these are simulations for the RC that I talked about in the previous video. All right, LC-Pi filters. So if you look at, this is the low pass LC-Pi. And if you look at this, you notice that obviously there's the capacitor and the inductor and capacitor. This creates the pi shape. But I've also included a resistance out here and a resistance down here. And I will explain why I added these resistances here in a bit. So this resistor here is a little easier to explain. So basically, if I did not have this resistor here, then this input would be in parallel with this capacitor. And this capacitor would not influence the transfer function at all. So what this added resistor does is allows this capacitor to form an RC circuit with this resistor right here. So this is going to form an RC circuit, and it's going to be cascaded with everything else over here. So everything else over here. Originally, if we consider that we don't have this resistor right here, we would just have an LC circuit. Now an LC circuit would have a resonance frequency where the reactance of the inductor and the reactance of the capacitor would cancel out. So then you would pretty much have a short here, which would cause the gain to spike up at the resonant frequency. And because I don't want my filter to have that resonant peak spike, I want to dampen my LC circuit to be an RLC circuit using this resistor. Now, when we think about dampening, we can dampen either overdamp, underdamp, or critically damped. And I'll talk about the damping a bit later, but we'll end up wanting to critically damp our RLC circuit. So, like I talked about here, the RC filter is in parallel with the RLC component right here. So the first part is we can just do the RC filter and cascade with the RLC. So this RC filter is a simple first order. We talked about RC filters in the previous video, so this has not changed. Now the RLC filter is what's a bit different. So I go through the math of the RLC filter using the derivative and transform the time domain, the S domain, all that stuff. Now what's different here is once we get the result of the RLC filter, we have this third component due to this additional resistance right here. It's in with this capacitor. And so when we critically damp our RLC circuit, we make it so that we have a repeating root. So basically, if I want to complete a square here, I basically just have to set whatever my resistance is to make sure I can complete the square. So in our case, if I can set this value equal to this, then I can complete my square. And where omega LC is going to be the square root of 1 over L over C, or square root of 1 over LC. Yeah. So with that, if I rewrite this using those terms, notice how I have this, and this can be simplified into a repeating pole or a repeating root here. So this is why it makes it easier, because with this repeating pole, we can, by completing the square, we can reverse Laplace transform it very easily. But anyway, I'll get to that reverse Laplace transform when we talk about the impulse invariance response. So for now, all I have to do is now cascade the high pass or the RC low pass filter with the RLC components together like this. So then I just stick them together like so. And so now we have the high pass filter LC pi. So it looks the same, except that instead where we had capacitors before, now we have inductors, capacitor, inductor. And the same thing like before, I've included additional resistors. So with these additional resistors, this creates the RL. This creates the RL circuit right here, and this creates the RLC circuit. So then the RL circuit is fairly straightforward. It's a first order, so you just perform the math where the omega is now R over L. Notice how this is similar to the tau constant. So this is similar to the tau constant, and then you have the RLC component, which is in parallel, so that we can perform the mathematics along with this. And similar to before, we can dampen our, because this LC, like before, would have a resonant spike, which would cause a spike in our filter response. So I have this extra resistance here to dampen the response. We want critically damped again, so that way I can have that repeating pole, which will make it easier to reverse the Laplace transform when we do the impulse invariance response. So critically damped here, so we end up with something that looks like this. So notice with the, just like with when we did the RC filter design for the cascaded, for the LC pi designs, I'm not looking at specific capacitor, inductor, or resistance values. Instead, I'm rewriting everything in terms of cutoff frequencies. So that way I design my filters based on the cutoff frequencies. So I don't explicitly know what my resistances, capacitances, and inductances are, but I know that when I combine my resistances, capacitances, and inductances, I'll get the cutoff frequencies that I desire. So using this type of design means that I don't have specific control over those values, but I do have control instead, or I control it instead through what I want the cutoff frequencies to be. So this is what it looks like, and I forgot to show that when these are cascaded, you just multiply them together. So if I take the original H1 over here, I copy it over here, and then I take H2, over here, I copy it. So this is what our overall transfer function is going to look like. It's going to, because since they're cascaded, it's just going to be them multiplied together. All right, so now we were talking about why we wanted that critically damped, so we can have that repeating pole, which will help make our life easier when we do the impulse invariance response. So for the low pass filter, similar to how we broke it up into the like the low pass filter, we broke it up to the RC and the RLC. We're gonna do the same thing over here. So now the RC, which we already know the Z transform, or the whole impulse invariance response process from when we did the RC filters, the inverse Laplace transform, sample it, and then Z transform. So here, since I critically damped it, I get this repeating pole at omega LC, or at the LC resonance frequency. And this is important because that allows me to control the cutoff frequency of my filter and makes it easier to inverse Laplace transform. So if I did not have this critically damped, then I would have to probably complete the square and do a bunch of other tricks to get the Laplace transform, to get the equation into a form that can be easily reverse Laplace transformed. But since I chose to critically damp my RLC circuit, it makes it a lot easier for me to handle. So then we transform this. So then when we transform this, then we sample it by saying t equals nts. I make this transformation right here to make it into a form that's easy to transform in the Z domain. And so now I transform into the Z domain, and I have this, and this gives me this. And so just like how we could cascade the two filters by multiplying them in the S domain, we can do the same thing in the Z domain. We cascade them by just multiplying the two Z responses together to get this. Same thing with high-pass filters. So for high-pass filter, the RL high-pass filter, even though it's a high-pass filter, you generally don't want to use the impulse invariance response for a high-pass filter design, but I went ahead in theory and did it anyway. Take the derivative, which gives you this impulse. So this is the RL, and then for the RLC, it's the same thing. Since I critically damped this, I can rewrite it like this, which makes it easy to inverse Laplace transform, except for the fact that they have this S squared, which means I have to take a double derivative, which is a headache, because then with each derivative, the derivative of the step function is a delta, so I have to remember those extra delta functions. So I simplify all this down, And then I make this transformation to help me make it easier to transform the Z domain. And so then I write it all out here. And so then, just like before, we can cascade the two by multiplying the two transfer functions together. So notice how I didn't actually bother to write out by hand what the actual product of these two cascaded filters are. And that's because just like with the RC filters that we discussed in the previous video, I don't have to multiply them out by hand because I can use MATLAB's convolution command and write the coefficient vectors and then just convolve those coefficient vectors to have MATLAB do the multiplication for me. So this was the impulse invariance. Now the bilinear transform is also pretty much the same. You make this substitution. Oh wow, it got small. This got small, so let me just increase the size of that. So you make this transformation, and again, I didn't bother to combine these because I can combine them using the convolve command. And same thing with the low pass filter. Do the same thing when we perform this transformation. Oh, I did not complete this transformation. Am I using an outdated? Am I using an outdated one because I thought I did update this one. But, if not, then I'll quickly do it. Oh, this only has the videos. Okay, so that means everything's in the other place. All right, so I guess I didn't complete this one, but that's not a big deal because I can quickly complete this one right here. So for the first section, since omega LC, this is squared, I know this is going to be the denominator part, so it's going to be the denominator section. Raised to -1, this quantity is squared. Over here, we're going to have this section squared for that, multiplied by the numerator, z minus 1, this squared, plus 2 times omega LC. So the S, we're going to have 2 over TS multiplied by 1 is going to be the numerator, 1 is going to be the denominator. -1, and then plus omega LC squared. This is going to be the numerator. Squared. That's for this section. And then for this bottom section, this one's going to be relatively short. I just take omega RC. This is going to be the denominator, 1 plus c raised to 1. This is going to be 2 over TS multiplied by the numerator, which should be 1 minus z raised to the -1, plus omega c multiplied by 1 plus c raised to the -1. And now it's too big, so this is probably why I need to shrink the size on this. Well, anyway, we can look at it in MATLAB because I definitely haven't updated in MATLAB at least. So here we are in MATLAB with our LC filters. So I think I start from the bottom because I started writing these functions from the bottom upwards. Yeah, so impulse invariance LPFs. So I have the RC component and I have the LC component. Just move this over here. Impulse invariance. So let me go back up here. So notice how I have this RC, because this is the RC section right here. So it's got the omega RC over Fs, and then it's got the RC denominator, which is going to be 1 minus alpha. And so then I have the scaling factor, just like before. And then for the LC numerator, I have alpha LC with this coefficient in front. And then for the denominator, I have this down here. For the impulse response of the high pass filter is the same thing, even though I don't think I use this because the high pass filter, you don't generally want to design a high pass filter using impulse invariance, but I just did it for the sake of theory. Basically, I just copied down this equation for the RC and this equation down here for the LC. And then with these as DC scaling factors. So next we have the bilinear high pass filter. Bilinear high pass filter looks like this. So because I was extra lazy, I noticed that the numerator is just 1 and -1. The denominator here is going to be 1 and 1. So then I just do these convolutions to get those coefficients. And then I can multiply it with the necessary coefficients in front. So like for this, I have this k, which is equal to 2 over ts plus this 1 minus z squared. So with this, I have this right here. Oh, this is for the RL. So for the RL, I have, yeah, this 1k times this z numerator, which is this 1 negative 1. And for the denominator here, I have k times the z numerator plus the omega RL times the denominator, and it'll automatically perform all that for me. And then I see the same thing for the numerator, or for the LC. I skipped the LC. I did these RC, but I forgot to do the LC. So this is the k squared with the numerator, convolved with the numerator. This is kc with numerator, convolved with the numerator, plus 2 times k omega LC with numerator times convolved with the denominator to multiply them. This is with the denominator squared. So that's how I can quickly generate those without having to do a bunch of math and algebra, by letting MATLAB take care of that for me by knowing how to use the convolution for polynomial multiplication. So for bilinear is pretty much this, bilinear transformations. All right, so bilinear low pass filter looks like this. I have the LC part, which has the numerator omega squared. Again, I use the same trick as before, where I just have the numerator and denominator coefficients, and so that I can convolve them as necessary. I do the same thing here. So this is this numerator squared, so that's why I have numerator convolved with numerator. This is going to be numerator convolved with denominator, and this is going to be denominator squared by this convolution. Same thing. Now we look at the RC side. The RC side has WRC times just the numerator. It has K times the numerator plus R omega L times the denominator. And so then I have to just convolve these two. So convolve the RC with the LC, do the scaling, and this is bilinear low pass filter. Bilinear high pass filter is the same thing. Let's see. What did I do for the bilinear high pass filter? Oh, where's the bilinear high pass filter? Oh, it's down here. So same thing. I have the numerator and denominator. I generate everything that I need to. Oh wait, no. This is the bilinear. Oh, I talked about the bilinear. I don't think I actually included the impulse invariance high. No, I didn't include the impulse invariance high pass filter. It's right here. So this is the impulse invariance high pass filter. It basically just is copy that equation. I think I already went over the bilinear high pass filter on accident, but yeah. So with that, we should be good to go on all 4 of our filters. Then we just need to cascade them together. So that's pretty straightforward. You just use convolution again to cascade the high pass filters. Then you cascade the denominators. So this is cascading high pass filters. This is cascading. Let me make sure. I want to confirm something real quick. So yeah, this is cascading the impulse invariance high pass filters. This is cascading the impulse invariance low pass filters. This should be cascading the bilinear low pass filters by just simply taking convolution. this one should take cascade bilinear high pass filters by using the convolution. All right, so we're over here. I'm going to change this to 8,000. So I'm going to have, just like with the Cascade RC filter example, I'm going to have a bandpass filter with a high cutoff frequency of 3,000, which is controlled actually by the low pass filter, and then I'm going to have a lower frequency of 1,500, which is controlled by the high pass filter. So here I generate the cascaded bilinear LPF, cascade HPF, bilinear LPF impulse, and then HPF bilinear. Wow, I did not I did not label these consistently, but so we can test the bilinear transform by convolving the bilinear low pass with the bilinear high pass, and then scaling it, and then we write this out to bilinear. So now for the impulse invariance, like I said before, we won't be using the impulse invariance of a high pass filter because that's generally not recommended. In theory, it works. I don't think when I tested it in practice, it didn't work very well. So instead, I'm just going to use the bilinear transfer or the bilinear high pass filter again. And so then I scale those and then I write those out into code composers. So I could go over the figures again, but I think I will save that for a separate video, just like how I did with the cascaded RC filters, and go straight into code composer for now. So with code composer, let's do, well, I already have cascaded LC bilinear open over here, so I'll just close all these out and make sure I'm opening the right one. Open the DSP config file, set the sampling frequency. I can see what my coefficients are. Oh yeah, I forgot to talk about the order. Since the LC pi filters had 3 LC components, either 2 inductors, 1 capacitor, 2 capacitors, and 1 inductor. Overall, there's 3 components, which means it creates third order filters. So since I'm cascading 2 of these together, that's going to create a 6th order filter low pass and a 6th order filter high pass. So with those 2 6th order filters, I combine those together and get a total of a 12th order filter. So the total filter order is going to be 12. I'll talk about all the roll-off rate and all that stuff in a separate video where I just go over the in-depth analysis on MATLAB, just like how I did with the RC filters. So for now, we're just going to quickly demonstrate this. So this has not changed except for the order. The buffers have not changed really. The code has not changed. We still read, we still do dot product, we still shift using the shift register because I did not have enough time to learn how to use pointers in an efficient manner for a circular buffer. But luckily, one of the advantages of IIR filter design is that we need less coefficients. So I can afford to be less efficient because I don't have to perform as many calculations. So I can be less efficient with my register. So I'm going to run this through debug. And this is for bilinear, by the way. So this is done building. Alrighty. So now we can pass through some signals. So since it's 1500 to 3000, if I put a 1000 signal, oh, let me turn this up. There it is. It's attenuated. And then if we put a 500 hertz signal, we'll be even more attenuated. Oh, can't even hear it, I don't think. Yeah, can't even hear it because it's so quiet. But if I send in a signal like 2000, you can hear it clearly because this is in the passband. So this is going to be our bilinear transform. Filter. So now we can also go to our LC cascade impulse invariance. So if we go to impulse invariance over here, I configure the DSP processor with 8 kilohertz. The code here in the ISR is the same, 12th order, same dot product, same shift register. That does not use circular buffer, unfortunately. Coefficients are still here. They're written using this code over here, just like before. So we're ready to run the debug on this one. So if I take the 1000 hertz signal, that stereo gets attenuated because it's in the pass band, or not in the pass band. It's not in the pass band. It's starting to get decayed because it's in the stop band, but you can still hear it. 500 hertz signal you can't hear because it's too far out that it gets attenuated so that it's inaudible. I can bring in the 2000, and you can clearly hear the 2000 because it is in the pass band. So that's going to be our cascaded LC-Pi filters. In the next video, I'll go in depth on the frequency analysis and all that in MATLAB in a separate video because I found that was easier, just like how I did with the cascade RC filters.